Good day everyone. So for today I will be discussing about increasing and decreasing function and the first derivative test. But before we start, let me ask you something. So what do you think is the importance of increasing and decreasing function? Okay, so let me give you this situation. Suppose that the total confirmed number of COVID-19 cases is monitored every 3 days. So through graphing, we can determine if there is an increase or decrease on the cases in each interval. So we have here the graphical representation of the COVID-19 cases in China. So from this graphical representation, we can say that the number of cases increases from January 21 to February 11. Okay, so let us now define increasing and decreasing function. A function f defined in an interval is increasing in that interval if and only if function of x sub 1 is less than function of x sub 2. A function f defined in an interval is decreasing in that interval if and only if function of x sub 1 is greater than function of x sub 2, where x sub 1 and x sub 2 are numbers in the interval. So if the function is either increasing or decreasing on an interval, then it is said to be monotonic. Okay, so we have here our illustration. So let us try to determine if which of them is increasing and decreasing. So as we can see here in our first illustration, our function of x sub 1 is lesser than the function of x sub 2. So therefore, this first illustration is a type of increasing function. So we will now proceed to the next illustration. So as we can see, function of x sub 1 is greater than the function of x sub 2. Therefore, this is an example of decreasing function. So we learned that the derivative of the function measures the rate of change, and we can use it as a tool for determining the intervals where a differentiable function is increasing and decreasing. If the graph of f has tangent lines with positive slopes over an interval, then the function is increasing, while if it has negative slopes, then the function is decreasing. So as we can see here in our illustration, if the slopes is less than 0 or negative, then the function is decreasing, and when the slope is positive or greater than 0, then the function is increasing. Okay, so note that we can get the slope by obtaining the first derivative. So if our f prime x is less than 0, then the function is decreasing, but when our f prime x is greater than 0, then the function is increasing. So we have here our theorem. Let f be a function that is continuous in a closed interval a, b, and differentiable on an open interval a and b. Then we have here if our f prime x is greater than 0 for all x in an open interval a, b, then f is increasing on a closed interval a, b. So if we have f prime x is lesser than 0 for all x in an open interval a, b, then f is increasing on the closed interval a, b. This theorem tells us that the derivative conditions are only required to hold in closed interval a,b, though conclusions apply to the entire interval. The application of this theorem is the proof of first derivative test for relative extrema of a function, which states that let the function f be continuous at all points of the open interval a,b containing the number c, and suppose that f prime exists at all points of the open interval a,b except possibly at c. If f prime of x is greater than 0 for all values of x in some interval, having c as its right endpoint, and if f prime x is lesser than 0 for all values of x in some open interval, having c as its left endpoint, then f has a relative maximum value at c. If f prime x is less than 0 for all values of x in some open interval, having c as its right endpoint, and if f prime x is greater than 0 for all values of x in some open interval, having c as its left endpoint, and f has a relative minimum value at c. So we will explain it. So the first derivative test states that if f is continuous at c and f prime x changes its algebraic sign from positive to negative, As x increases to the number c, then f has a relative maximum value at c. And if f prime x changes the algebraic sign from negative to positive as x increases through c, then f prime x has a minimum value at c. So here are the steps to determine the relative extrema analytically. So first step is to compute f prime x, or the first derivative. Next is to determine the critical values of f, that is the values of x for which f prime x will be equal to 0, or for which f prime x does not exist. The next step is to apply the first derivative test. So let us have some example. Okay, so we have here our first sample problem. Plot the graph of the function defined by f of x is equal to x cubed minus 6x squared plus 9x plus 1. First thing to do is to find f prime x. We have our f prime x here. We have 3x squared minus 12x plus 9. Then we need to determine the critical values of f prime x. So we have 3x squared minus 6x plus 9. So we need to factor it out to find the zeros of the function. So we have 3x minus 3 and x minus 3, and we have x is equal to 3 and x is equal to 1. Okay, so we can determine the critical values by equating this to 0. So we have here 3x minus 3, it will be 3x equals 3, then over 3. So x is equals to 1. So that's why 1 is the critical value here. Then x minus 3, x is equals to 3. So that's how you determine the critical values of f prime x. So let's proceed to the next step. So here is we need to determine intervals. So we have the critical points 1 and 3. So if we write a number line, this will be 0, 1 will be here, 3 will be here. The numbers on the right side of 3 is to positive infinity, while the numbers to the left side of 1 is to negative infinity. So we have here our intervals. We have negative infinity to 1, 1 and 3, and 3 to positive infinity. So let us write our f of prime x here first. F prime x is equal to 3x squared minus 12x plus 9. Okay, so all we're gonna do is to substitute. Okay, so all we're gonna do is to substitute the test points on our f prime x. We have here negative 2. If we substitute negative 2, we can have 3 times negative 2 squared minus 12 times negative 2 plus 9. So we have 3 times 4 plus 24 plus 9. We have here 12 plus 24 plus 9. The result is positive, so f prime c is positive. Erase muna. Prime c. So we'll try the next test points for the interval 1, 3, which is positive 2. So okay, so we have here now 3 times 4 is equal to 12 minus 24. It will be negative 12 plus 9 is equal to negative 3. So the f prime c here is negative for the interval 1, 3 with the test point 2. And next is we have the interval 3 positive infinity with the test point 4. So we need to substitute 4 to our f prime x. Okay, we have here 3 times 4 squared is equals to 16 minus 12 times 4 plus 9. We have here 3 times 16 is equal to 48. 12 times 4 is equal to 48 plus 9, so that gives us 0 plus 9, and our answer is positive 9. So f prime c is positive. And note that if f prime c is positive, then the function is increasing. But if f prime c is negative, then our function is decreasing. So it is written in the conclusion and here. Okay, so we can now conclude that in interval negative infinity to 1, the function is increasing. And for the interval 1 and 3, the function is decreasing. And from the interval 3 to positive infinity, the function is increasing. So we have now our graphic. From this, we can now graph the function. And here's the graphical representation of the function. You can see in what intervals did the function decrease and what intervals did the function increases. Let us now proceed to our next example. Given the function f of x is equal to x squared minus 5 if x is less than or equal to 3, and 9 minus x if 3 is less than x. So we need to find the relative extrema of f by applying the first derivative test. Determine the values of x at which the relative extrema occur, as well as the interval in which f is increasing and decreasing. So the first thing to do is we need to find f prime x of this function. So we have f prime x will be equal to derivative of x squared minus 5 is equals to 2x, then copy lang if x is less than or equal to 3. And we have here the derivative of 9 minus x, it is negative 1 if 3 is less than x. So we now have here our f prime x. So we need to find the critical numbers. Note that as x approaches 3 from the left and x approaches 3 from the right, they are not equal. Then the limit does not exist, and we can consider 3 as a critical number of the function. And if x is equal to 0, f prime x will be also equal to 0, since we have here 2x, because 0 is less than 3. So if x equals 0, then it will be 0. Therefore 0 is also a critical number. So our critical numbers here is 0 and 3. So the next thing to do is we need to determine the interval. So we have here again, we need to write number line, and we have here 0, and this will be 3. This is positive infinity, negative infinity. So this is our intervals. We have negative infinity 0, 0, 3, and 3, then positive infinity. And we also have x is equals to 0 and x is equal to 3 to determine minimum and maximum value. Okay, so the next step is obtaining the test points. So for negative infinity to 0 is we have negative 1. For the interval 0, 3 we have 2, and from the interval 3 positive infinity is we have 5. So okay, so let us now copy first our f prime x. That is equals to 2x if x is less than 3, and negative 1 if 3 is less than or equal to our x. So we have our test points, negative 1. So negative 1 is less than 3. So we have substitute the 2x. We have 2 times negative 1 is equal to negative 2. So our f prime x is negative. So if we have positive 2, we also have the 2x because 2 is less than 3. So we have 2 times 2 is equals to positive 4. So our f prime x is equals to positive. And we have here 3 to positive infinity. So we have our test point, which is 5, and it is here. And if 3 is lesser than or equal to our x, so we have here, if 3 is lesser than or equal to x, we have negative 1. So our f prime x is equal to negative. And note that if it is negative, then it is decreasing, and if f prime x is positive, it is increasing. So we can now conclude that it is decreasing on the interval negative infinity to 0, increasing on the interval 0 to 3, and decreasing at the interval 3 to positive infinity. We can also notice that when x increases to the number c, where our x is equal to 0, it changes the algebraic sign of f prime x from negative to positive. So if we try to increase the value of x, if we have x is equals to 1, the sign of our f prime x will be positive. Therefore, we can conclude that in x equals 0, we have a relative minimum value. And in x equals 3, we can notice that if f prime x changes algebraic sign, if we increase the x, the algebraic sign will change from positive to negative. So we can say now that x has a relative maximum value where x is equal to 3. So we have now here the graph of our piecewise functions. As we can see, it is decreasing in the interval negative infinity to 0, and it increases in the interval 0 to positive 3, and it decreases again on the interval 3 to positive infinity. So as noted in the table previously, we have relative minimum value as x is equals to 0. So as we can see, our minimum value is here, where x is equal to 0 here, 0, and we have our relative maximum value at x is equal to 3. So our relative maximum value is here, where our x is 3. So that's how we get the relative minimum value and the relative maximum value by using the first derivative test. That could be all.